Hello everyone, my name is Shariq. I'm an MS PhD student at Visual Computing Center at KAUST. I'll present to you our work on depth estimation using AdaBins, also named as AdaBins.
The task of depth estimation is to estimate distance from camera of each pixel in the given image, say for example in meters. The result may look somewhat like this. Depth estimation is a classic task used in several applications, from self-driving cars, robotics, and even Mars rovers, to applications in social media, like this cool effect on the cat here, and more recently for this social distancing surveillance. Current works struggle with estimating distributions of depths present in a scene, mainly because the distributions vary a lot. For example, this close-up image has depth values concentrated in a small subinterval of the depth range, whereas other images contain a wide variety of depth values and others in between. This extreme variability further increases the complexity of this task. We propose to solve this using the adapt-to-binning strategy. There are various ways to divide a depth interval into bins or buckets. You have a uniform division where each bin is of equal width, or a log uniform division. We can also try to learn this division of buckets for a given dataset. But all these variants are fixed at inference time, meaning that no matter the input image, the division is always going to be the same. But in contrast, we propose to have adaptive bins which can change with each input image. This is the overview of our final proposed architecture. On the input side, we have a single RGB image, and the model first estimates the adaptive bins for this given scene, and then uses that to estimate the final depth. The idea is that we can estimate the adaptive bins required for the input scene by extracting the global information using a patch-based transformer. We use this transformer on a high-resolution tensor output from a convolutional encoder-decoder. This transformer module we call MBIT gives us two outputs, a high-resolution tensor that we call range attention maps and our adaptive bins. We then estimate the probability distribution over these bins for each pixel and then take the expected value, giving us the final depth map. Note that this framework is very general and we can use any encoder-decoder like architecture here. And to the best of our knowledge, this is the first design to use transformers for a pixel-wise dense prediction task. We use chamfer loss for the adaptive bins that pushes the bin centers closer to the ground truth values, as shown in this illustration. We use the standard SI log loss for depth maps, which is very common in depth estimation works. This is a video showing how the model has learned to change the density of predicted bins adaptively according to the input scene. Note that the bins are estimated first and are then used to come up with the final depth map. Observe how the model changes the density of the bins according to the input image by focusing on smaller ranges for close-up scenes and then distributing the density for others. And since we take the expectation over the bins, we get much smoother depth maps compared to the prior works that also use discretization. Our model outperforms all the state-of-the-art methods across all the datasets. These images are from the Kitty dataset. You can observe the differences, for example, here on the signboard. We also test generalization capability of our model by training on one dataset and testing on another. Our model significantly outperforms all the prior methods in this task. Our architecture also shows reasonable out-of-distribution performance. Note that the model has never seen close-up images of faces, but it's still able to resolve among the parts of faces and the background. That's all from my side. Thank you so much for your time.